Hello everyone, welcome to my channel Chemical Engineering Knowledge. In the previous lecture we have discussed about the molar Flowrate balance algorithm in the microreactor. So we have microreactor. We discussed that microreactor are used for explosive product. It is also used as a chemical sensor. We also discuss the importance because the specific surface area in the microreactor is very large and there is low resistance to heat and mass transfer in the microreactor. We also discussed a reaction between nitrosyl chloride, chlorine and nitric oxide. So there was a gas phase reaction and the width of the reactor was given to us, the height of the reactor was also given to us, the length of the reactor was also given to us. This was our microreactor. The pressure, this was the pressure, this was the temperature, and nitrosyl chloride is converted into nitric oxide and chlorine gas. This was our reaction. This was the symbolic form of the reaction. This was the symbolic form of the reaction. A was limiting reactant, and this was the final symbolic form of our reaction. The given data was also given to us. This was the temperature 698, 1641 was pressure. Our NaCl was converted into NO and chlorine. FA0 was given to us 22.4 micromole per second. 22.4, and the rate constant was also given to us at 500 Kelvin. So we use Arrhenius law to determine the rate constant at 698 Kelvin. We assume that the reactor is a flux flow reactor, that the microreactor acts as a flux flow reactor. 35% of A was converted into B, so A was 98 for the 85%, and there was a question that plot and analyze molar flow rate is a function of the reactor volume down the length of the reactor. There was another question that find the volume of reactor at 85% conversion of A using Polymath. So this was the mole balance. Step number 1, we use mole balance. We use mole balance on component A, and this was the final mole balance, final product of the mole balance. The mole balance on component B was this one, and for component C the mole balance was this one. So this was step number 1, mole balance component A, mole balance on component B, mole balance on component C. In the second step, we assume that the reaction is elementary. Reaction follow elementary rate law. So minus Ra was equal to Ka into Ca to the power 2, because this was 2 in the stoichiometric position, and the reaction F is a reaction follow elementary rate law. In the third step, we use the relative rate law. Minus Ra divided by minus 1 is equal to Rb divided by 1, Rc divided by 1 plus 2. This was the relative rate law. And in the step number 4, we determine the relation between the concentration and flow rate. Concentration and flow rate of component A. This was the relation between concentration and flow rate of component A, and this was the relation between concentration and flow rate of component B. This was the relation between the flow rate and concentration of component C. We also determine C by using the ideal gas law. C is equal to PRT. So this was C0 was equal to P0 P0 value was given to us, this one. R is given to us, gas constant, the temperature was 698, so Cp0 was 0.286 mole per dm cube was obtained. We ignore step number 5 because there was no pressure drop in the microreactor, so we ignore this step. This step was ignored. In step number 6, we combine the mole, we combine the mole valence with rate, and this rate was given to us, and we put the Ca is equal to Ct0 into Fa divided by Ft whole square, because there was 2 on the Ca term. So we use this term, this step. Similarly, for component B we use this relation, for component C we use this relation, Ct0 square Fa Ft, and there was a question that used Polymath to find the relation between flow rate and volume of the reactor. So in the second question, find the volume of reactor at 85% conversion using Polymath. So this lecture, this video is given in the description. You should watch this video. After this video, in this video we will use Polymath to find the relation between flow rate and volume of the reactor. So first of all, open Polymath. This is Polymath. Use the come to program. This is the linear equation, non-linear equation, the differential equation. So differential equation. Click on differential equation. This interface will open. Now click on this term, enter a new differential equation, click on it. So we will put the differential equation A divided by Fe divided by Fe is equal to Ra K0. Initially the rate of component A was 22.6. We have determined this in the previous lecture. In the comment, you can write anything in the comment. So this was suppose equation number 1. On done. Then click on this one, enter the second differential equation. H B divided by B is equal to RB. Initial value of B0 was 0 because power A was constant, and initially there was no B and no C in the reactor. So in the comment section, this is equation number 2. So this is equation number 2. Come to enter the third differential equation. dFc divided by dV is equal to RC. X0 was 0. This is equation number 3. Now enter the explicit equation. So the explicit equation are you can enter the explicit equation like the other value. Temperature was 698 Kelvin. Don't write the unit of temperature because you know that the temperature is in Kelvin. Similarly, write the Ct0 value is equal to Ct0 is equal to P0 divided by RT. So the value pressure was 1641 kilopascal divided by the value of R is 8.314 into multiplied by the temperature. So multiplied by this temperature 698. Then put the activation energy. Activation energy is divided by E is equal to 24 kilocalorie per mole. So 24 kilocalorie can be equal to 24 24,000 kilojoules per mole. Then put the Ft, the total flow rate. Ft is equal to Fa plus Fb plus Fc is the total flow rate. Then enter the value of Ca. Ca value is equal to Ca. Ca is equal to Ct naught. Ct naught. This Ct naught. This one. Ct naught into multiply by Fa. This one, divided by Ft, this Ft. Then put another equation, which is the rate constant K, using the Archimedes rate law. K is equal to K naught. P to the power exponential to the power P to the power E divided by R. So E divided by R. This is the gas constant. Multiply by 1 divided by 500, given temperature. The temperature at which the rate constant was K naught, this one, minus 1 divided by T. So this gives the temperature at which the rate constant value is K, if we want to determine. So this one. Then, so there is error of this verify after function use variable experiment. So this we will remove this power. So this parameter now we use another bracket. Now if a naught value is given to us, if a naught value is given to us, this one, 22.6. The V naught value is given to us. V naught is equal to, we know that V naught is equal to Fa naught divided by Ct naught, because flow rate is equal to concentration multiplied by volumetric flow rate. This is the volumetric flow rate. So it is the flow rate of component A, molar flow rate of component A divided by the concentration, total concentration, Ct naught. This Ct naught, this one, Ct naught. Now the curve space time phi is equal to volume by volumetric flow rate. Volume of the reactor V divided by the volumetric flow rate is V naught. This V naught, this one. So this V naught is the V naught. This V naught. Now put the, there is undefined variable RA, RB, RC, FA, FB, FC, K naught, R. So define RA. RA is equal to this RA, this in equation number 1, the rate of disappearance of component A is obtained from element to rate law K multiplied by RA is equal to minus K into CA square. So the K value is this one, this, multiplied by C A, this CA, which is equal to CP naught multiplied by FA divided by FT to the power 2. Now conversion is 85%, conversion is equal to X is equal to 1 minus FA divided by FA naught, FA naught by FA naught. So FA naught. Similarly, RB value is undefined variable RB/RC. So RB is equal to, from relative rate law we know that RB is equal to minus RA. So there is undefined RC, FA, FB, FC, K0 and R. So undefined. So RB is equal to minus RA and RC is equal to minus RA divided by 2. So this was now undefined FA, FB and FC. So this FA value, here we written FA in small, so this value small a, put small a, small b and small c. So FA cannot value is undefined, so FA, the FA value here is, this one is small FA, this one is small FA, this small FA, and here C is also small c, small ca. So cannot value, the cannot value is unknown to us. The cannot value is given, which is 0.29, and the given data we put 0.29. So FAR and CA, the R value is 1.987. So FA and CA is undefined. This is the small FA naught, small FA naught. This also small CA naught. FA naught value is unknown, so it is also small FA. Everything will be small. If you want to write everything in capital, you can also use. So this is simple naught. FA naught values, and this is the small FA naught. Now the FA value is unknown, so FA value is, this should be not, so there is one unknown FA, undefined variable FA. So this FA is will be also written as wrong. Remember, if you write, you should write everything small or large. This should be written small because this FA is small, this FA is also should be also small. This FA should be also small. This FA could be also small. This FA could be also small. This FA will be also, because every term is different. There is a relation between various variables and various equations. So now initial and final value of independent differential variable is not set. So independent variable is volume. So initially value for the reactor is 0 dm cube and the final value is 0.10 raised to power minus 5 dm cube. So the final volume of reactor was 0.10 raised to power minus 5 dm cube. So it can be written as 0.00001. 0.00001. So this is the final value. Now ready for solution. So you can plot graph table, click on it, click on table, click on report, and this one solve. Click on this arrow. So it will take some time. This is the calculated variable of differential equation. C as CT naught, initial value, final value, FT 26 is the final, 33 RA RB. So this was V naught. This is the differential equation. These are the special equation. These are the general instruction. You can also check the graph. Minimize it. This is the graph. So you can change the font size. Click on this y-axis and the y 0.00 30 and the x-axis you can also change 10 raised to power and also 10 raised to power minus 5 this one, the final value. You can also add the grid line. On the grid line scale, you can select the scales. Here the title. In the title you can write micromole per second, micromole per second, and micromole per second. These are of A, F, B, F, C, A, F, B, F, C. You can also click on these. These are the values. You can also label. The volume is dm cube. So dm cube. You can OK. The volume in dm cube is open. You can close. This is the table. This is the design. These are the curves. So you can design. In design you should connect the points, auto scale, draw marker. So draw marker, then the curve width, you can increase the width. The marker scale is the border width. You can increase the border width and click on close. So this was the relation between this one is the FNR. This is the FA, this one, from 22.6 it suddenly decreased to 0 or it is suddenly decreasing. Similarly, this is the FAB, LB, ZB value is increasing as you see. This is the FC value also increases. So this is the relation between the flow rate and the volume of the microreactor. So at 85% conversion. So when FA, this is FA0 value is 22.6. So when 85% conversion, then the FA0 M21 minus 0.85, the value will be come to 3.39 up to this point. So what will be the reactor volume at which there will be 3.3, when the molar flowrate of 123 is 3.39. So what will be the reactor volume? So we can check from this graph. Come to this graph and we can suppose at this point the volume of reactor is the volume, the molar flow rate of container is 3.39. So at this volume, at this place, the reactor volume will be 3 multiplied by 10 to the power minus 6 billion cube. So this is the relation between the FA0 and reactor volume, and the reactor volume at which conversion of component A, this component A is 85%. So you can change the value of activation energy. This is another table. So this is the table. Now you can change the value. For example, I can pick it 226. You can also check it 226. Suppose I 24. I will put 24 in this place. Then click on solve. You will draw this graph. In the table, this is the graph. Axis, scale, the font. You can change the font size, the time range, New Roman, variant. So this is the grid line, the curves. The title you can micromole mode per second. You can write anything mode per second. This is the design marker, and this is the size. You can marker scale, you can increase or decrease 100, so it will be 100, it can be 60 is correct. Now this is the table, this is the curve and function. This is the curves and function. So you can remove FA like this one. You can remove the FC. You can add FA, FB, FC, and then layers. So similarly, you can change. You can suppose this is 300. The minimum value of x is 0 and the maximum value of x is 0.0001. 0.0001. The minimum value of suppose of y is 0, this one, and the maximum value here is 300. So I want to increase it to 250. So 250 you can apply. So 250. You can also like 230, yeah, so it's the 230. So this is the relation between, this is the FA values decreases in the reactor volume. This is the 10 to the power minus 5 dnq. So this is the level dnq. Okay, close. So this is the graph shows the relation between the FA volume, FB volume of reactor, and FC and volume of reactor. And FA0, the FA0 value here is, I think this place the FA0 value is 3.39. Suppose the FA0 value at this point is 3.39 mole per second. So at this point the volume of reactor will be 7.00 multiplied by 10 to the power minus 6 billion cube. So this is the volume of the reactor at which 85% conversion of A is occurring. So this was just Polymath. You can solve it in other software, organic differential equation solver. Thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.